Hello students and welcome to lesson 7.02 Acid and Base Reactions. Before we jump into the lesson, just real quick I want to mention the common core standards that we are covering with this particular lesson. You can access all of the common core standards by going to course information, selecting standards, and then it will have all of them listed for all 8 modules. For this particular lesson, our objectives is to predict the products of the acid-base reaction, explain neutralization, and then solve an acid-base stoichiometry problem. To have a successful experience in 7.02, we do need to have completed 7.01. In that lesson, we were defining bases, identifying acids and bases, and naming them. So if you have not already done so, please make sure you've completed 7.01 prior to completing 7.02. So with no further ado, let's go ahead and jump right into it. When we take an acid and base and react them together, we call that neutralization. Reason being is because we are reducing the acid and base properties of each of those reactants. So they are becoming less acidic, less basic, thereby becoming more neutral. When we use the Arrhenius acid and base theory that we talked about in 7.01, it is simply a double replacement reaction that produces water and salt. So if you look here at the example that we have on the screen, we have HCl plus KOH yielding H2O and KCl. If you remember back in 7.01, we talked about when you have H at the beginning of the compound, you have an acid. When you have OH at the end, you have a base. So basically what happens is just a typical double replacement reaction where the first two elements, the cations, switch positions. So now the H is actually going to be with OH, which we typically write that as H2O. Okay, so we have HOH, which again we usually write that as H2O. And then we have the K combining with the Cl. Okay, so again the K just swaps positions. The K now is over here with the Cl, and that H is now over here with the OH. So these are our two products. So we have water and we have a salt. In this case, our salt is potassium chloride. All right, now I just want to mention here that when we say salt, we're not just talking about table salt. We're not just talking about NaCl. Okay, salt is technically any metal combined with a nonmetal. Generally speaking, it's going to be your group 1s and 2s with your halogens, group 17. Okay, but those are our salts. In this case, again, potassium chloride. All right, now the problem though is that the Arrhenius definition cannot always be used when describing neutralization reactions. Usually we like to use the Bronsted-Lowry theory, and sometimes we even have to use the Lewis theory because it covers more of those different types of reactions out there that are considered neutralization reactions that are not necessarily just straight up regular double replacement type reactions. In the Bronsted-Lowry theory, which is one that's most frequently used, remember that the acid is a hydrogen ion donor, whereas the base is a hydrogen ion acceptor. So when we look at the example on this screen, what we have to look for is who's donating hydrogen, who's giving it up, and who is accepting. So in this example, if we look down here at the bottom, we see we got HCl. And then over on the right side, the H is no longer with the Cl. The H is with the CO3. So that means going back here at the beginning, the H had to have been donated to the HCO3, and the Na is replacing it. So that gives us the H2CO3 and then the NaCl. So that means the HCl is the acid and the NaHCO3 is the base. All right, so again, the most common one that we use is the Bronsted-Lowry. We're looking for who's donating hydrogen and who's accepting the hydrogen. Okay, the donator is the acid, the acceptor is the base. All right, now before we look at some more examples here, just want to mention some real-life examples of neutralization reactions. A very common thing is when you're in a lab, you may have even heard this in safety discussions in your traditional schools where they talk about if you spill an acid, you want to clean it up with a base like baking soda. And just the opposite, if you spill a base, you typically clean it up with an acid like vinegar. Okay, so that's a use of it. More everyday type of use would be the second one here, antacids. Antacids are simply bases that when you consume them, it neutralizes the acid in your stomach, and of course by neutralizing the acid you decrease the upset stomach feeling that you have. Another one that we see a lot is plants. Plants sometimes are better suited for acidic soil, while others are better suited for basic soil. So if you have one that wants to be in more basic, we might add some lime to it to lower the acidic level or neutralize it. Where if we go the other way, we can use sulfur to help neutralize the basic soil. So you may have heard of people liming their gardens before, and that's why, because they're lowering the acidic levels, getting it closer to neutral, so that their plants will have a better time growing. All right, so just some real life examples there. Okay, so now let's look at these examples here and try to identify the acid, base, and the salts that are being produced. Okay, in the first one, again, we're looking for who's donating and who's accepting. So we want to compare what we start with, the reactants, with the products that we end up with. So on this first one, we see we've got HNO3. Over here on the right side, we have NaNO3. So on this side, on the right side, it is without hydrogen. So that means it must have given it up. So the HNO3 is donating that hydrogen to the NaOH. And this one actually does follow the Arrhenius theory, because that NaOH is then going to replace the H with the NO3. So for this example, the HNO3 is our acid, and that is called nitric acid. And the NaOH, sodium hydroxide, is the base. And of course we know the water, H2O, which means NaNO3, this must be our salt. And remember earlier I said that when you have a metal with a nonmetal, that is a salt. Well, here we have a metal with a polyatomic ion, and that is also a salt. Polyatomic ions can replace the nonmetal ion, or it could replace the metal ion. Okay, so this is our salt, sodium nitrate. All right, let's try the second one. We have HBr plus NaHCO3, sodium bicarbonate, and this is hydrogen bromic acid. Kind of gave that one away there. All right, but if you, again, looking at where we start and where we end, here we have HBr. Over on this side, the Br is now with the Na. So that means the Br had to have given up the hydrogen. So the hydrogen is given up to the HCO3. And this one again happens to be a double replacement again. They don't all end up that way. Replaces the H. So the HBr is our acid. Sodium bicarbonate, that happens to be baking soda, is the base. And then on this side, which one is the salt? Well, H2CO3, it starts with an H, and if you go through your naming rules, you would know that this is carbonic acid. So we actually produced a different acid. And then we have NABr. Well, NABr is a metal with a nonmetal. So this one must be our salt. Okay? If you are thinking salts seem to be ionic compounds, you are absolutely correct. They are. Salts are ionic compounds. All right? And then one more example. On the bottom here we have HC2H3O2 with SrOH2. So again, we're comparing the reactants with the products. If we take the C2H3O2 and look for it on the product side, we see it is now combined with the Sr. So it had to give up the hydrogen to do that. So again, the hydrogen is leaving and the Sr is replacing it. So the first one here is the acid, and the second one is the base. Okay, so our acid here, this happens to be acetic acid, vinegar, and this is strontium hydroxide. Okay, now for the products, of course, H2O is water, which means this must be our salt. And again, we have a metal combined with a polyatomic ion. So that would definitely be our salt, because the polyatomic ion is taking the place of the nonmetal. All right, so that's how we identify the acid and the base. Compare the reactants with the products, and figure out which compound gave up the hydrogen in order to become the product that you're seeing. And that'll be your acid, and then of course the one accepting that hydrogen will be the base. Now in 7.03 we're going to talk more about how we can actually experimentally determine the concentration of an acid and a base. In this lesson, though, we're going to focus on the stoichiometry behind how we would actually calculate that. So stoichiometry, remember, is back in Module 4, Module 5, and even a little bit in Module 6. It works the same way. We got to first have our balanced equation. We got to then take what we're given and convert it to moles. We do the mole ratio and then take the new moles and convert it to what we need. So it's the same process, we're just using some different numbers here when we're dealing with concentration. The second thing I did want to mention here is this technique on the bottom. All right, we're going to again get into this in 703, but there's a technique called titration that we can use to, in a lab setting, determine the concentrations. So we'll talk more about that in 703, but basically we use special equipment that allows us to add a known acid or base, a known concentration of that acid or base drop by drop until we get a neutralized reaction. And we know when it's neutralized by using either a pH indicator or a pH meter. And again, we get into both of those more in 703. But basically an indicator will change colors depending on if it's an acid or a base. And then the pH meter is just like any other type of meter. It will tell you an exact number for that pH value. And that's all in 703. So for right now, we're just going to focus on the first thing here, the math, the stoichiometry in determining the concentration in a neutralization reaction. So let's just jump right into an example. Okay, if at 32.62 milliliters of calcium hydroxide with an unknown concentration is neutralized by 35.0 milliliters of 0.321 molar HCl, what is the concentration of the CaOH2? Well, again, the first thing we got to do is get a balanced equation. That's always going to be our first thing. So for this one, we've got HCl reacting with calcium hydroxide. Alright, so again, it's a double replacement reaction. So the hydrogen and the calcium are going to switch partners. So now we have HOH, right? We have H plus ion with the OH minus ion. Plus 1 minus 1, they cancel, so we just leave it HOH, but again, we like to write this as H2O. Plus the calcium, which is in group 2, so it has a plus 2 charge, with the chlorine, which has a minus 1 charge. So when we crisscross those, we end up with CaCl2. Alright, so you can see we're going back to Module 3 here with writing formulas. Everything ties together. Now, we have to balance it. Right now on the left side I have 1 Cl. Over here on the right side I have 2 Cl's in the CaCl2. So if I put a 2 in front of the HCl, that balances up the chlorines. Alright, now if we look at the hydrogens, we've got 2 hydrogens here with the HCl, and I've also got 2 over here with the CaOH2. So total, I have 4 hydrogens on the reactant side. Alright, 2 and 2, so I got 4 total. Over here on the product side, I only have 2. So, if I put a 2 in front of the H2O, 2 times 2, that gives me my 4 H's. Now those are balanced. Now that 2 also distributes through to the O. So I have 2 times 1, I have 2 oxygens. Over here, I have 2 times 1, I have 2 oxygens. So those are balanced now. So there is my balanced equation. Now I want to take the information out of the word problem and write it underneath the reaction here. It tells me I have 32.62 milliliters, and I want to determine the molarity. And then for the HCl, it tells me I have 35 milliliters, and it is 0.321 molar. Alright, so we have to first take what we're given. We're given HCl, both molarity and volume, and then we need to convert that to moles. Well, to do that, we need to do a couple of things here. First off, we need to remember that molarity, going back to Module 5, is actually moles per liter. Second thing we need to do is we need to convert the 35 milliliters to liters so that we have everything in the same units so we can actually cancel them out. So going back to Module 1, we need to remember that there are 1,000 milliliters in 1 liter. So that's going to give us 0.035 liters of the HCl. Now let's go ahead and do that for the calcium hydroxide real quick, because we're going to need that in liters also, again, so that we're all in the same units. So we take the 32.62 Alright, and we're going to divide that by 1,000. So we're going to have 0.036, it's supposed to be a 6, there we go, 2 liters of the calcium hydroxide. Okay, so now we can actually do some stoichiometry here. Now we've got everything in the correct units. All right, so we're going to take the volume of the HCl, and we're going to multiply that by the molarity to get the moles. All right, so we're going to have 0.321 moles divided by 1 liter, and that's going to get us moles of HCl. Right, step 2 is the mole ratio. Again, we get the mole ratio from the balanced equation. So when we look at our balanced equation here, we have 1 mole of the CaOH2 and I have 2 moles of the HCl. All right, now that we have moles of CaOH2, remember molarity is moles divided by liters. So for our last step, all we have to do is divide by the volume, 3,262 liters, and that will give us the molarity. So going back here, you can see all the units will cancel out. Liters of HCl cancel out here. Moles of HCl cancel out here with moles of HCl, leaving us with moles of CaOH2 over liters. So it's 0.035 times 0.321 times 1 divided by 2 divided by 0.03262 liters, and you would get, for a final answer, 0.176 molar CaOH2. All right, and that's how you would do the math for figuring out the concentration of an unknown acid or base in a neutralization reaction. And we will use this not only here, but we also use it in 703 when we do the titrations. Alright, so what you'll need to do now is, of course, go into 702, make sure you've completed all parts of the lesson, and make sure you do any practice problems and examples. If you still need some help, attend the open tutoring sessions. We also have a review sheet in the Resource Center you can use. Once you feel comfortable with the material, you then go to the assessments or gradebook section and click on the quiz and go ahead and take that quiz. And hopefully this was a helpful video, and we will see you back again for 703.